Good, thank you. So many of you do not know me because I come from the field of neutron stars and high energy astrophysics. So white dwarfs are new to me, so give me a bit of a credit here. So this work, this talk is based on two works. First, Lyutikov and Tunen, where we discuss the model of fast blue optical transients. And the second one is 2022, where a few confirmed predictions. So one of the first shocks to me was that the rates of white dwarf mergers, there is at least three different rates per white dwarf, per stellar mass, per galaxy, and so on. In any case, the white dwarf merger rates are huge, and is the most unobserved, the most frequent unobserved catastrophic event. And type 1As may account for a small fraction of those. And interestingly enough, those mergers are not observed directly, except for maybe type double degenerates of type 1A. And that's interesting because it's catastrophic in a sense. It involves, two solar masses of mass. So there is a large room for many interesting transients after the merger, especially with Super Chandrasekhar. And what I will discuss is this fast blue optical transients. And I will argue that these are rare but bright results of white dwarf mergers, followed by accretion-induced collapse maybe 10,000 years later with small remaining envelope. And the emission is central engine, newly born neutron star powered. So a quick review of fast blue optical transients. They're very short. They peak at few days. Peak luminosity 10 to the 44, 45, similar in optical and X-rays. Change of properties at about 30 days. Hydrogen line appears. There is rising infrared component. This interesting one that was triggered by second paper is first they saw an X-ray flash at 35 days that was predicted. And secondly, the whole energetics is dominated by X-rays 1 year after. This is exceptional even by gamma ray burst standards. Okay, so few quick conclusions. Very short peak times. It's not nickel powered. So there should be small ejecta mass, less than 10% of a solar mass, even less, maybe even 1/100th of a solar mass. And it's hard to beat the numbers here. So how to make small ejecta masses? Secondly, energetics is almost 10 to the 50 with X-rays a year after. It must be in central engine, internal engine powered with luminosities 10 to the 43 ergs per second a year after. So these are two quick conclusions. So the idea is a merger of regular white dwarf with neon magnesium. The less massive one is disrupted, forms a shell. That shell loses energy to the wind and adds mass to the core. And under certain conditions, accretion-induced collapse will occur. And again, under certain conditions, the neutron star may be born in the center. That will produce powerful wind that will first have to go through the ejecta and then through the preceding wind. Okay. So, and let's work out different steps in this scenario. First, population synthesis. There are two evolutionary channels that can lead to tight oxygen near magnesium and regular white dwarf. There are then unstable gravitational wave-driven mass transfer. Carbon-oxygen white dwarf is disrupted, no type 1A. Then you start shell burning, mass loss, core growth, accretion-induced collapse. And by that time, we started with maybe half a solar mass of envelope, but it was losing a lot of mass. So very little may be remaining. And these special F-bots are lucky ones that had very little envelope left before the accretion-induced collapse. If there were heavy envelopes, it would be weaker and longer and harder to see. Okay, so population synthesis, as I mentioned, 2 evolutionary channels. The rates are okay. The merger delays, it can be as short as 100 million years, so fairly fast. So that's also good. Then what we have here is a neutron star in the center producing a wind. And the wind will be shock, and the shock will produce photons. And those photons will be diffusing out. And you can calculate their diffusion. And basically, at first, nothing happens. And then suddenly, they all break out. All of the photons, basically, all of the photons emitted before the breakout time, they break out almost simultaneously because they're trapped, and then suddenly they're free. Well, almost. It's a diffusion. It's not a free propagation. It's a diffusion. So, and you can do a little bit of Monte Carlo. That's the green function. That's a point explosion. If you continue injecting, then of course after the transparency, you will have flat. But if our central star slows down, then there will be a declining light curve. Since they are blue because this is the shock that produces these photons is radiation dominated, meaning the energy of the flow goes into photons. And the estimate of the temperature is 40,000, highly independent of the parameters, almost independent of the parameters. And that's indeed what is seen at 40,000 Kelvin. Change of properties at 30 days. 2 things happen approximately then. First, you have a full transparency through ejector. Photons just fly straight. And second, you remember we had an envelope ejector and the wind. And it's about time when the shock breaks from the envelope into the wind. And in the first paper, we predicted that there should be some kind of X-ray event during this breakout because the envelope is very dense and thick and the wind is less dense. And indeed, it was seen by the Rosetta at about time that we predicted. And later on, we have a powerful pulsar and a very dense, powerful wind. The pulsar produces highly magnetized wind. Through synchrotron emission, you produce X-rays in the shocked wind, but also you drive the forward shock in the ejector, and you can produce infrared in the, not injected, the wind, pre-explosion wind. Okay. Spin synchrotron, that's what you kind of expect. Then a late pickup in infrared is because this whole thing expands and particles at first are very fast cooling. But later on, since things expand and the magnetic field falls down, they enter in a slow cooling region. So they all pile up and they pile up and produce emission more in infrared. Another good thing is that in a fast cooling regime, all the energy that the shock puts into particles is emitted into radiation. So very high efficiency. And the parameters that you need are not extreme. They are kind of not simple, but not extreme. And second, also there was this erratic X-ray variability, and that can be explained. You probably heard about 10 years ago, there was the flares in the Crab Nebula. So these are kind of mini reconnection, mini jets within the neutron star driven wind. So that can be explained. Also, in infrared, here is a light curve at 34 gigahertz. It's increasing, while at 200 and 300 it's constant. And that's because ejector contributes a lot to free absorption. So the high frequencies are transparent from the beginning, while the lower frequencies, what we see here is just the surface of tau 1 expanding. Okay, so few possibly related phenomena. There is this IRAS source which is very hot, extremely luminous star, and both the star and the nebula free of hydrogen and helium. And the expectation is that this thing will go as F-bot. Then highly magnetized and rapidly rotating white dwarf as small as the moon. That's the one where it was about to collapse, but it ran out of the envelope. Ultra poor white dwarf is a doubly burnt ashes, the ones that didn't explode also. And also, if the larger ejector mass, you expect more energy just go into PDV work, and it will be on transparency on longer time scales and less efficient conversion into photons. So predictions, and so the merger proper, the merger of white dwarfs, it should be an optical event with energies around 40 ergs lasting few hours, maybe a day. Unfortunately, transient searches are not designed for that. They usually look for longer. The main prediction is that this whole system should be hydrogen poor. And it's too hot in the beginning to conclude. Some hydrogen is seen later on, but it's very difficult to put a constraint. So very advanced radiation modeling needed, and few people that tried when at my request when they were not able to do it. So maybe somebody in the audience could. There should be evidence of interaction with the pre-explosion wind, anisotropy isn't expected. Pre-F-bot archival data may show a bright, persistent hydrogen-poor source, like the one that I mentioned. And you may also see the remnants of the wind, of hydrogen-poor wind, but that is limited to maybe a few thousand years. There may be some connection to gamma ray bursts, to short gamma ray bursts that are not. There may be another channel for short gamma ray bursts. For example, there are this bursts where it's a short burst, but with a tail, and the tail has tail that goes for 100 seconds and has more energy than the initial short burst. So, main points. Small ejector masses, competition between the wind and ashes added to the core. Overall energetics is dominated by the central engine, not nickel decay. Fast cooling, very efficient conversion of energy into radiation. And also nearly all the photons escape at the same time. Breakthrough the ejector X-ray bump, merger proper. That's the people do not look for that, because most, actually all optical transient searches, they are based on supernova-like curves, meaning days and weeks. But and it's there are many asteroids that flash, and so it's very difficult to do it. But there should be optical flashes of these values. Okay, that's it.
Top questions? Yeah, just what do you think the probability is maybe that one of these mergers could lead to something like accretion-induced collapse to a black hole? Is that something that is plausible, and would you be able to have any features that would tell you this is what's happening?
Well, for white dwarfs, Chandrasekhar mass is a pretty good limit. For neutron stars, it's not. But for white dwarfs, it's Chandrasekhar mass. So unlikely, I think. Yeah.
Because the total mass of the merger, right, you could have something over 2 point something. I mean, what? Maybe I missed it. Did you show the?
Yeah. Yes. So the core will collapse at the Chandrasekhar mass, right? There will be still some shell left, but most likely it will be ejected.
Okay, thanks.
Yeah.
I want to ask about host galaxies. So my understanding is most F-bots have low mass, low metallicity, star-forming host galaxies, but I'm guessing this would predict older, more
Yes, that
massive
was
host
the
galaxies.
point we were making here, that these are delay times of merger. So there's a very broad distribution of delay times. So basically, we can accommodate any host.
But yeah, wouldn't that be similar to type 1a host galaxies?
Not necessarily. Yes.
Okay.
Yes.
Oh. Yeah, thanks for your talk, Maxim. Could you find these maybe in the disappearing white dwarf survey? I mean, they just disappear and don't come back? Or are they too faint?
Sorry, I didn't get it.
Keaton talked about the disappearing white dwarfs survey, right? So these would quickly flash and then disappear as well. So could you find them, with similar techniques? Basically look for white, or are they too faint pre-merger that they're not actually disappearing white dwarfs?
I don't think so, because I think the talk was you look for, you're looking at a white dwarf and then it's gone.
Yes. So
Here, you're not. Here it's the other way around. There was a bright star, but it was nothing special. And then there is a flash, a few hours long flash.
And then it's gone.
And then it's gone. Yeah. Oh yeah, right. Yes. Yeah.
I mean, just to be clear, Keaton's survey is in the galaxy, right? So, yeah.
Yeah, the rates, yes, here it is. Again, this is for population synthesis. So this is the rate. I think it's about, so if the rate, so if this rate is correct, then it's one merger, white dwarf merger for this specific smaller, so it will be about 1 per 1,000 years per galaxy.
Thanks for the talk. So sorry if you said this and I missed it. So for the 18 Cal, there's persistent radio emission also. Is there a natural way to account for that through this scenario?
Yes, so the pulsar winds, neutron star driven winds, they produce a lot of radio pulsar. So basically, this model is something like a pulsar wind nebula, but in an expanding envelope and wind. So yes, you do expect that radio emission, and importantly, I base it on not on the forward shock, but on the wind termination shock. That's how pulsars produce emission from radio to X-rays, particles accelerated at the termination shock. So yes, radio is very natural in this scenario.
Let's thank Maxim again.